Hi, this is Dr. Liu. This question is an equilibrium problem. We have a horizontal bar, that's right here. It has 1.2 meters long and mass 12 kilograms. It is hinged on the left side, so here's a hinge, and it's pulled at the right end by a cable. So here's the cable. Now the cable makes 32-degree angle, theta, with the horizontal. And then a 15 kilogram store sign is suspended below the bar at a distance 0.14 from the right end. So find the magnitude of tension that's along this direction. So first we need to define our axis of rotation. So let's draw the forces on the diagram. We have here's one force. Let's change color. So we have here tension, and we also have, this is forces on the bar. So here the store sign is pulling down. Right, so there's the force of store sign. The store sign is here. There's a hinge. The hinge pulls the store sign vertically up and also horizontally pushes to the right. So here's a vertical force from the hinge and also a horizontal force from the hinge. If you wonder why there's a horizontal force, just imagine there's a big hole here in the wall, and which way would the bar go? The bar would just go into the hole, right? So the hinge prevents that bar from going into the hole. That means it has to hold the bar, push it toward the right. At the same time, it has to lift it up. Lifting up part is easy to understand, right? And the bar itself has its own gravity, so that's from the center and pulls down. Gravity. So there are 1, 2, 3, 4, 5 forces. So the choice of axis rotation should minimize unknown forces torques. So I'll have a few choices here. Here's A. Here's B. And here's C. Here's D. So 4 different choices. Let's see. If I choose A, these two forces are originating from A, so they will not have any lever arm. And so I'll have 3 forces with lever arm. This is an unknown force with a lever arm, so it's not too bad to choose A. So what if I choose B? Well, gravity of the bar does not have any torque. The horizontal hinge force also does not have any torque. So this is not too bad, but we're left with 2 unknown forces having torques. Okay, so let's move on to C. If I have C as axis of rotation, then force from the store sign and this horizontal hinge force will go through that point. They'll now have torques. So that's roughly the same as choosing here, except that I will have no torque from the store sign, but I'll have torque from the bar. So what if I choose D then? If I choose D, the horizontal hinge force has no torque. The tension, which is at an angle, has no torque. And these 2 forces have torques, but that's not too hard. The forces are known quantities. And this vertical force has torque, but it is perpendicular to this direction, so it's easy to calculate the lever arm. And this is also the only unknown torque. So this choice has its advantage. Compared to A also has some advantage because these 2 unknown forces have no torque. But you have to find out the lever arm of this tension force, which requires you to draw an angle, right? So let's choose D here. So once the D is chosen, I realize lever arm of tension is 0. Also, lever arm of the horizontal force is 0. And lever arm of the vertical force is the entire bar's length. Okay, so lever arm of the vertical force is the length of the bar. The lever arm from the bar's gravity should be halfway across. So lever arm of gravity is L over 2. Then lever arm of the store sign is just that distance d over here. I actually defined that d intentionally to make it easy to calculate with this as axis rotation. Okay, so let's imagine we would just hold this point, everything else can move freely. So these two forces tend to pull the bar down to make a rotation in this direction. So that will be positive torque. And that force pulls the bar up, that rotates this way. It is clockwise, so it is in negative torque. Okay, so we know that net torque equals torque from gravity of the bar, torque from the store sign, and then torque from the vertical hinge force. And that is equal to rotational inertia. Acceleration is equal to 0 because of equilibrium. There's no acceleration. Okay, so gravity's torque is Fg times Lg. Store sign's torque is gravity of the store sign. Lever arm store sign. Torque from the vertical force is vertical force times lever arm vertical force. 0. Okay, so now let's plug in the values. The Fg is m of the bar times g times L over 2. Then the store sign is m of the store sign, g. Lever arm store sign is equal to d. Then vertical force, lever arm vertical force is entire L equal to 0. So we know everything except for the vertical force, so we can solve for it. So vertical force is equal to everything divided by L, and this will be mg over 2. And this is mg d over L because I divided everything by L. If you want, you can factor out gravitational constant. So the left side is, well, this first term is mb over 2. The second term is ms times d over L. So let's find this value. 9.8. The store sign is 12 kilograms over 2. And sorry, not store sign, this is the bar. The store sign is 15 kilograms times distance is 0.14. And then the length is 1.2. So this is our vertical force. Let's use our calculator. So 9.8. Okay, so 12 over 2 plus 15 times 0.14 over 1.2, close parentheses. So we have the vertical force is 75.95, so 76.0 newtons. Okay, so now that we have this force, we can use this force in free body diagram. So we have a total of 5 forces here. This force tension needs to be decomposed in our diagram. The other forces can be just brought together into a diagram. So let's do that. Let's just bring them together. If I can just copy and paste. Okay, I even got that dot from there. So now I'll do copy this and I'll paste it over here and just move them together. Okay, and I'll do this one now. Okay, that's not good. Paste it further away. That's interesting. Okay, here's tension. There's one more, is this gravity here. I'll keep this slightly offset so we can see there are two forces down. Alright. So we'll do a horizontal and vertical axis. Okay. X. Vertical axis, I'll try to run it here. Y. And I can decompose this tension into Ty and Tx. So here's Tx. Here, very close to vertical hinge force is Ty. Let's rewrite that. Okay. So because of the equilibrium, all the forces are balanced. So I can have the net force. Let's use net force symbol. Net force in X. We have a horizontal force to the right. We have a tension to the left. I guess I should have drawn them a bit closer to being equal in lengths, but that's okay. Alright, and we also have this angle here, the theta angle. So this equation turns into the horizontal force minus tension cosine theta equals 0. And from net force in Y, we have quite a few. Vertical hinge force, tension's vertical component, and two downward forces. And that's also equal to 0. So we have vertical force plus tension Y should be tension sine angle minus these two forces they're going to sum up into the total gravity bar store sign G equals 0. Okay, from equation 2 we should be able to solve tension because we already know the vertical force. Right, so from equation 2, the vertical force T is equal to, if I divide out the angle sine, the angle is 32 degrees. And then I can add this total mass gravity to the other side, subtract that from both sides. So that is mass gravity here. So 12 plus 15 times 9.8 minus vertical hinge force 76. Okay, so let's use Python. I don't think I loaded the that module, so let me just run this. Okay, so now I have sine function loaded. Also in degrees, so that's convenient. Okay, so now we have the 12 and the 15, the 27. So 27 times 9.8. And then minus 76. And close parentheses. So we have a total of 356 newtons. And if your question is what about the horizontal force, right? Well, now we have tension. We can put it in equation 1. So the horizontal force is tension times cosine theta, 356 times cosine 32 degrees. And we can calculate that as well. So that's 356 cosine 32 degrees. So we have 302. As the horizontal hinge force. We also calculate the vertical hinge force to be 76. Alright, thank you.